Good morning, afternoon, or evening. Okay, I don't have a preview here. Let me get it. There we go. So as you can see, Screencastify is not giving me the preview of the whole screen here for whatever reason now. So hopefully it's okay. I had to restart this because I was a little worried about that. So what we're going to look at today is gravitational field. So I kind of did notes already, so I'm going to open that up. Okay, and this is going to be day 11 here. And once this pops open, we will be looking at basically three things today. Okay, and I'll open it up here, and we're going to be looking at difference between two kinds of masses that there are, and we're going to be looking at gravitational field of the Earth, how we calculate it, and we're going to do some examples, and then Einstein's theory of gravity as well. Okay, so let's bring this back up where I was. Sorry, I had a problem, so I just kind of had to restart. So that's why it looks like this. Okay, so it's day 11, and we're in Unit 3 fields. We're going to look at two kinds of masses. We're going to develop the gravitational field formula and do a few examples of that. And then we're going to look at Einstein's theory of gravitation. That's our general idea today. So when I talk about something called inertial mass of any object, so an inertial mass of an object is a measurement of the object's resistance to force. Okay, remember that according to Newton's laws of force, net force is equal to mass times acceleration. Okay, so if we're talking inertial mass, take the net force and we multiply it by the mass and the acceleration of the object. The inertial mass then would just be equal to the net force divided by the acceleration of the object. So inertial mass is the object's resistance to force. Okay, and that's what we mean by inertial mass. And when we talk about something's gravitational mass, we're basically talking about its weight, for lack of a better word. Okay, it is a measure of the object's attraction to another object by gravity. Okay, the Earth is our other object because we're so close to the big mass of Earth. Okay, and this comes from Newton's gravitational law. So gravitational mass is completely different. If we take force of gravity, that's equal to g times the mass of the Earth times the mass of gravitational mass over r squared. If you rearrange that to get the gravitational mass by itself, it's force of gravity times r squared over g times the mass of the Earth. And this is called our gravitational mass. Okay, and it's going to be so many newtons of force for us, or sorry, I guess kilograms. Pardon me. Okay, and this is going to be question there. There's inertial mass. There's gravitational mass. Okay, and inertial mass we're talking about Newton's second law. Gravitational mass we're talking about Newton's gravitational law. Gravitational mass deals with the Earth as being the other object most of the time, unless we're on the moon or something. And inertial mass deals with the resistance to being accelerated by an object. Okay, so that's the difference between the two masses. Okay, again, I apologize that we had some issues there. I accidentally stopped the video and had to restart it. Screencastify is not giving me a good preview. It's just giving me a camera preview and not a full preview of the screen. But I did double check, and the screen preview should be able to see the second screen over here. Rather than just me, I just don't need to block anything out over here. Okay, so that's the first thing we wanted to do, was looking at those two different types of things. Are we going to be using these two formulas? Not really, but we just need to know the difference between the two. So then we want to talk about something called gravitational field. So we want to talk about the gravitational field. Now, basically, we're going to be talking about the gravitational field of the Earth. Okay, so let's kind of do a little diagram of gravitational field on the next page here. Okay, so let's say that we have this situation here. Let's draw the Earth here. Oh, where's my circle? There it is. Okay, so here's my Earth. Oops, that's too small. There's my Earth with the center. And in and around this, we have a gravitational attraction of the Earth, attracting. I guess we should use arrows there. Everything gets attracted to the center of the Earth, no matter where you are. Okay, and these are gravitational field lines. Okay, so I'm just going to kind of fan it out all the way around. Everything gets attracted to the center of the Earth. I should probably use a different color here. Okay, so yeah, I'm going to do that. I'm going to use a different color. So let me just, because that'll be too confusing if we just use the same color for the whole thing. Okay, so let's do it right in the middle here. Oops, I got to change the circle again. Oops. Sorry, guys. All right, let's start with the circle again. All right, so let's start with right in the middle here. Little dot. Okay, so that's the center, and there's my Earth. Now, if we take, and we'll change color this time, so it's a little, if we take and draw all the gravitational field lines that's attracted to the center of the Earth. Let's do it. Okay, so these lines doesn't want to give me a color here. There we go. So if we come in to the center of the Earth and just draw these field lines here all the way around, going to the center. This represents the gravitational field around the Earth. There we go. That should be good. Okay, so this represents the Earth here. Let's label this up. Okay, there's the center of the Earth. And these red lines that I drew here, or purple, I guess, this represents a gravitational field line. Okay, so as you can see, as you get closer and closer to the Earth, to the center of the Earth, the gravitational field lines get closer and closer together, right? So out here, they're far apart, right? But in here, right on the surface of the Earth, they're theoretically, if they're evenly spaced, they're going to be so strong. So as you get farther and farther apart, the field lines get farther and farther apart, meaning that you have a weaker gravitational field. As you get closer and closer to the center of the Earth, the field lines get closer together, and therefore you have a stronger field. Now, generally speaking, we consider at the surface of the Earth, everything has the same gravitational field strength, even though you're on a mountain or so, because that is such a small distance compared to way out in outer space that nothing changes, that there's a negligible change in the gravitational field strength of the Earth in a kilometer or two, right? But if you go out thousands of kilometers, then you're going to have a change in the gravitational field strength. So underneath that, let's just summarize that. Oops. Let's get this all set up a little better here. Okay. The closer the gravitational what did I'm gonna move that down because I'm going to block myself up. The closer the gravitational field lines are, the stronger the field. As we see, closer you get to the center of the Earth, the stronger the field. I guess we should say the gravitational field. We consider the surface of the Earth to have a constant gravitational field strength. I know that there's that thing in the corner, so let me move this up. It's probably blocking you out there. Okay. We consider the surface of the Earth to have a constant gravitational field strength as the thickness of the crust or the surface of the Earth, and where it changes from mountains to flat is negligible. Is not negligible. It is insignificant, I guess. When you look at the large distances. So we're talking about the radius of the Earth. And there's spell right here. Okay, because there's such a difference between. So going out an extra 5 kilometers doesn't change the gravitational field strength that much. But if I go up 2 times the radii of the Earth, then it'll change it for sure. Okay, so as we saw with our diagram, when we're out here, the field lines are farther apart, so there's a weaker field. When we're right on the surface of the Earth, it's fairly even though my picture isn't perfect or 100% perfect. Okay, and let's derive the gravitational field strength formula. So we can derive the formula from inertial mass and gravitational mass. So we know that force of gravity, according to Newton's laws, okay, equals mass times acceleration. Okay, and this acceleration that we're talking about, we're going to say that this is the g value, okay, of the Earth. Okay, so when we're talking about force of gravity, that's m times g. Okay, 9.81, we know newtons per kilogram. Where do they come from? That? Okay, we also know that force of gravity, according to Newton, okay, and this is an object, okay, is equal to g times the mass of the Earth times the mass of the object divided by r squared. So if we equal these two out, we can get the gravitational field strength formula. So we're going to take these two and equal it to this. Mass of the object times the gravitational field strength equals universal gravitational constant times the mass of the Earth times the mass of the object divided by r squared. So we can see that the mass of the object eliminates itself. Sorry, guys. So then we come up with the gravitational field strength. Okay. So G times the mass of the planet or Earth times r squared. This represents gravitational field strength formula, and it'll come out in newtons per kilogram. Okay, so G is the gravitational field strength. That's newtons per kilogram. Okay, G is the gravitational constant. Okay, and that's at 6.67 times 10 to the negative 11. I always forget what the unit is here, so let's just take a look here. Newton meter squared, kilogram squared. Okay, m is the mass of the Earth. Okay, it could be a planet if you're talking about a different planet, or the sun, or if you're talking about the moon. Okay, but traditionally it's the Earth if we're talking about the Earth. And r is the distance from the center. Okay, so that's basically the gravitational field strength formula. Okay, so the surface of the Earth, we know that it's 9.8 newtons per kilogram, and that comes because the radius of the Earth is relatively consistent all the way around. It slightly varies by a few kilometers here and there, on a mountain or in the ocean or something like that. So it'll be slightly different, but not very, very significantly different. Okay, so let's do a basic problem example using this gravitational field formula. Okay, so say a satellite orbits the Earth at 308 kilometers above the surface. find the gravitational field. On the satellite. From the Earth. And we'll say that the radius of the Earth is, let me look it up here. The radius of the Earth is 6.38 times 10 to the 6 meters. Put it in kilometers. And the mass of the Earth mass of the Earth 5.97 times 10 to the 24 kilograms. Okay, key things that we have to remember when we're doing this is that everything has to be in kilograms. Oops, wrong one. Everything has to be in kilograms, everything has to be in meters, okay, and that kind of thing. So if we draw this out a little bit, here's the Earth. There's the satellite around the Earth. There's the radius of the Earth as well. Okay, so if we want to find the gravitational field strength, okay, just what we derived, this is equal to G times the mass of the Earth times or divided by R squared. Okay, so we have to figure out what R is in meters, and we know what the mass of the Earth is up right there. So first of all, R equals 308 kilometers plus 6380 kilometers. Okay, so if we do that, then we have to change it to meters, of course. Okay, so we end up getting 6,688 kilometers, or 6.688 times 10 to the 6 meters. Okay, or 6,688,000 meters. Okay, so then we have to use our equation. So G we know is gravitational field strength. Okay, gravitational constant first. Okay, and that's, again, I always forget that one. Newton meter squared, kilogram squared. Okay, and then we multiply that by the mass of the Earth. So one of the kilograms is going to be gone. We're going to be left, and then we divide it by did I put the R in the wrong place? Probably did. Gravitational field. Oh no, put it in the right spot. It's good. And we're going to divide by the meters. Okay, so that's going to cancel the meter squared out and one of the kilograms, and we're left with newtons per kilogram. Okay, so the first thing we should do is figure out the top. So 6.67 exponent negative 11 times 5.97 exponent, scientific notation exponent 24. Okay, I'm not going to round anything off. Keep it on the calculator and then round off at the end. Okay, and then this one is 6.688 exponent 6 squared. Okay, so then our gravitational field strength of this particular one, 3.89199 to the power of 14 divided by 4.472. Notice no rounding at all here. Otherwise, we'll have errors. Okay, so I end up getting 8.90. So if we go newtons per kilogram. So if you're 308 kilometers above the Earth's surface, then there's a slight change in the gravitational field strength. It goes from 9.8 to 1 newtons per kilogram to 8.9. Okay. Now, thickness of the crust isn't that big, right? It's only about 6 kilometers, I think, at the thickest point. So if you thought about that, that would only make a difference of putting a 6 there, right? You could see how much different that would be if you're interested. Okay, so that's a little bit about that gravitational field strength. They might actually ask you a similar question. Sometimes they might use the moon here. So then they have to give you the mass of the moon and the radius of the moon. Okay, let's try that one actually. Okay, what is the gravitational field strength on the Earth's moon? Okay, we're going to use Google. Find mass of the moon and the radius of the moon. You probably just look up the concept too, but we're just going to find out what it is using those two. Okay, so let me do that on here. Okay. Mass of the moon. Okay, mass of the moon is, okay. Let's get this right here. There we go. Mass of the moon. Okay, according to Google, it's 7.3776730 9 times 10 to the 22 kilograms. So let's go to three significant figures. 7.35 times 10 to the 22 kilograms. Okay, and the radius of the moon. Okay, let's look that one up. According to Google, the radius of the moon is 1,737 kilometers. Okay, so now if we're going to calculate this, we're going to get what is the gravitational field strength on the moon, on the field strength on Earth's moon. Okay, and we're talking about being right on the surface. Okay, so the gravitational field strength of the moon is going to equal, what was it here? G times mass of the moon times the radius of the moon squared. Okay, so and our numbers are 6.67 times 10 to the negative 11 Newton meters squared per kilogram times the mass of the moon was 7.35 times 10 to the 22 kilograms divided by, okay, now we have to change this into 1.737 times 10 to the 6 meters, because it has to be in meters. So we'd have to add another 1,000 onto it, and then if we did it scientific notation, that's what it would be. So 1.737 times 10 to the 6 meters squared. Okay, so now if we'll move this up. If we do the gravitational field strength of the moon, or on the moon's surface, okay, 6.67, scientific notation negative 11, times 7.35, scientific notation 22. Okay. G of the moon. Okay, so the top one is 4.90245 times 10 to the 12, all divided by 1.737, scientific notation 6, all squared, 3.017169 times 10 to the 12. Okay, so if we divide those two together, your gravitational field strength on the moon would be 4.90245, scientific notation 12, divided by 3.017169, scientific notation 12. Okay, those will give us 1.624 or 1.62 newtons per kilogram. So if you ask the question, you're going to be quite a bit lighter on the moon, right? Because 1 kilogram on the Earth would weigh 9.8 newtons, and on the moon it would be only 1.6 newtons of force. So there's a difference between. Okay, according to Google here, they're saying that, I guess they rounded up. They said that the Earth is 6,371 kilometers, and we've got 6,380. I guess ours is a little bit bigger than in the book that I'm using than the one that Google says. So that might be a little bit different, significantly. Okay, so that's basically looking at gravitational field strength. Okay, calculating gravitational field strength. The other thing is you might have to calculate mass of it as well. So let's do one example of that, and then we'll leave the Einstein's gravitational stuff till tomorrow. So about 5 more minutes. We'll do one more example. Okay, so let's say just because we found something on the moon, let's say something like this. What is the mass of gravitational we're talking about? Of an object okay, and we'll use that is, let's say, 10 kilograms on the Earth on. What is the mass of an object that is 10 kilograms on the Earth on the planet on Mars? We have to kind of calculate. Okay. Let's say given the mass of Mars equals, okay, let me look that one up. According to Google, that one is 6 point, oh, that's the same as the Earth almost. Oh no, it's different. Good. 6.39 6.39 times 10 to the 23 kilograms. And let's say, what is the radius of Mars? Okay, and the radius of Mars, we're going to look that one up. Okay, the radius of Mars is 3,390 kilometers. Can't get this thing to highlight. There we go. There we go. So what is the mass of this? That is, well, let's put this changes to 98 newtons per kilogram. I guess we can keep it at 10. That'll still work. Okay, so what we have to do is we have to figure out the mass. So if we look at our gravitational field strength formula of Mars, okay, that's going to equal G times the mass of Mars times over radius squared. So we're going to calculate the constant of G on Mars, and then we'll multiply it by the mass of the inertial mass on Earth. So this would be equal to 6.67 times 10 to the negative 11 times 6.39 times 10 to the 23 divided by 3.39 times 10 to the 6 squared. So that'll give us G, and then we can multiply it by 10 to get our so 6.67 exponent 11 times 6.39, 6.67 exponent negative 11 times 6.39 exponent 23. Okay, so that's 4.26213 times 10 to the 13. Okay, and then we got this one here on the bottom, 3.39 exponent 6 squared. So gravitational constant on Mars is let's see here, what do we get? 4.26213 divided by 1.14921. So you get let's go with two significant figures, 3.7 newtons per kilogram. Okay, so now we got to do a ratio between the two. So on the Earth, 10 kilogram mass on the Earth over mass on Mars equals G on Earth over G on Mars. Okay, so if you know that the mass of the Earth, mass of the object on Earth is 10 kilograms, okay, over something that's on Mars, and the constant on the Earth is 9.8, and on Mars it's going to be 3.7. So it's going to be less, obviously. So we do a cross multiplication. 3.7 times 10 equals 9.8x. Okay, and our x value, what's that going to be? Okay, divided by 9.8. So you're going to get about 3.8 kilograms on Mars. Okay, so we had to figure out the ratios of the gravitational constants, and then do a ratio of the masses. Okay, so we'll stop there because I went way too long today. Sorry, guys. That's been a good 45 minutes, so we'll have to stop there. I probably went right through on some classes, so my apologies.